In electrochemistry, we had to design our own scale and decide what was going to be our 0 point for our potentials. The original cell that we used for that was the standard hydrogen electrode. So we abbreviate that as the SHE, or she. The standard hydrogen electrode, though, is usually referred to as SHE, not she. E naught for that will be 0, since we defined our scale off of that. Now, we want to keep that in mind because anytime we use a different reference scale, we're going to want to make sure that we adjust our voltages to be back on this corrected scale. So we'll have to account for that voltage difference. Now, notice that what we've got here is we've got hydrogen gas bubbling at about 1 atmosphere, 1.00 bar. Those bubbles are now coming right along the surface of this platinum electrode, coming out to the atmosphere. Here in the solution around it, we've got some H+. I'll even specify that that's going to be at 1.00 molar. And actually, even better would be to refer to its activity, of course, because when we use concentrations, we're actually being a little dirty. The correct answer here would be to say we're using activity, which equals 1.00. Remember, we don't actually say molar when we're talking about activity. Then we'd have that connect to a salt bridge, and that would be the edge of our cell. So what I'd like you to do, go ahead and pause the video in a moment, and I'd like you to write the cell notation for this half cell. Okay, so let's take a look at that. Now remember, we're going to start from the surface of our electrode. So we're going to write platinum solid. We're going to show that there's a phase change. Now we're going to be going into hydrogen gas, which then goes to the H+ bulk. We specify that it's aqueous, and since we're saying that this is something that matters a lot for the construction of it, we'll even go ahead and write our concentration, or better still, activity coefficient, 1.00 molar. This is going to be the edge of our half cell. From here we'll have our salt bridge, and then we'd have the other half cell involved. So that would be our cell notation for the standard hydrogen electrode. Now this is what they look like when we do things with our normal beaker and wire sketch. But let's see what it would look like a little bit more authentically. So what we're going to have is a cylindrical mesh of platinum. And it's going to be some platinum wire. And typically it is pure platinum, though I suppose you could probably find something that might have platinum-coated wires. To be honest, I don't do enough electrochemistry to tell you if you'll find only pure platinum or if you'll find something with a difference out there on the market. Now, we obviously need a hydrogen inlet, so we're going to have a tube coming down, bubbling, a nice fine mesh of bubbles into that mesh of platinum. Our activity for the H+ ion should be 1.00 molar. We want to be at 25 degrees Celsius. And often they're going to show this in molal units, just so that we don't have to be concerned about any differences in density of water and things like that. Now, if we were to have oxygen in here in any amount, what we're going to have is oxygen binding onto the platinum surface, and it's going to cause other reactions and surface fouling. So to prevent that, we have it bubbling through a little airlock here. So we just fill it up with oil or water or something. It's going to be bubbling out, and we'll have this going to our trap line. That way we don't have our hydrogen gas building up inside of our hood. And then this spot down here is just going to be a little, usually a little stopcock here, so we can turn on and off our connection to the salt bridge as we're doing our experiment and as we're finishing for the day. So we'll have this open. It'll be connecting over here to the salt bridge, and that would connect this to our other side cell. So that's the usual construction of our standard hydrogen electrode.